Okay, well, welcome everyone to this week's physiology seminar. The speaker today needs very little introduction. In fact, he asked me to be very brief. So Tony Auerbach has been a pillar of our department for close to 40 years and has been well funded during that time. Tony is going to speak to us about his lifelong research passion, which has been dissecting the molecular events that constitute ACH receptor gating, from agonist to activation and inactivation. And he says that and speaking of gating states, at some point, Tony is going to show us a special image when he was in an early state primed to start his career. So without further ado, Tony, take it over.
Thank you, Tom, for that nice short introduction. Thank you, everyone, for tuning in. What Tom's referring to is at some point in this seminar, I'm going to show you a picture of my postdoctoral advisor before I came to Buffalo. So when Tom invited me to give this seminar back in August, I thought it was going to be in front of a live audience. So I like to gesticulate and walk around the room and make eye contact, and that's not going to happen today. And I do that in order to keep everybody awake. So finding the missing postdoctoral picture is a way of keeping everybody awake. So the topic is agonist deficiency, and the outline is shown here. There's 3 sections. I'm going to present some background information, which most of you already know, but I thought I'd bring everybody up to speed. Then I'm going to talk about efficiency, and then I'm going to talk about the link, the missing link that's been hiding in plain sight, sort of. And things go from simple to complicated in the course of this talk. So let's start with something simple. I hope we start with something simple. Something we all know, the dose-response curve. You increase the agonist concentration, and you measure the response, and you fit it to some empirical function. And since I'm going to be, this is a concentration response curve. And since I'm going to be talking about energy efficiency, I want to relabel these axes as energy in and energy out. So you're pouring in chemical energy in the form of agonist, and you're measuring response energy, which is complicated, but at the bottom of response energy is a conformational change of the protein to which the ligand is binding. So the receptor that I'm going to be talking about is a nicotinic acetylcholine receptor. It's a ligand-gated ion channel, 300 kilodaltons, 5 subunits surrounding a central ion channel. There are ligand binding sites in the extracellular domain, and there is a hydrophobic switch gate down in the membrane domain that turns the conductance of the pore on and off by joining the extracellular and intracellular water compartments. The receptor the subtype of nicotinic receptor I'm going to talk about is the vertebrate neuromuscular nicotinic receptor. The subunit composition is shown here. This receptor has 2 neurotransmitter binding sites that are equivalent and independent. By that I mean for the agonist I'm going to be talking about for the next hour, the binding properties are approximately the same, the 2 different binding sites, and these binding properties stay the same regardless of whether the companion site is empty or occupied by another agonist. So nicotinic receptors, of course, are very important in the nervous system and the immune system. They're implicated in a number of important diseases. But that's not going to be the topic of my talk today. We're not going to be talking about physiology.
Hey, Tony, your audio is cutting in and out.
What can I do about that?
I don't know.
Well,
now it's better. Probably a little less hand motion, Tony.
I gesticulate. That's what I do when I talk. Okay, so we're not going to be interested in the physiology so much. We're going to be interested in the ACH receptor as a model system, as a model receptor for understanding receptor theory. And it has been a magnificent model receptor. Starting back in 1905, it's the first receptor to which the word receptor was given. It was actually coined by Langley in 1905. And all these things on this list are first identified and studied in acetylcholine receptors. So basic concepts as affinity and efficacy were first identified in acetylcholine receptors. And I hope by the end of the talk you will think that it's okay to put efficiency on this list as well. So we're going to start with this right here. The ACH receptor is an allosteric protein. I'm going to use a very simple definition of an allosteric protein. It's a bistable protein that has 2 native states with different functional outputs that have different affinities. Now, we're talking about receptors, so we're talking about binding energy here as the input. But if voltage-gated channels, mechanical channels are also allosteric proteins, so you can replace affinity by whatever stimulus energy is appropriate. So what I'm showing down here are potential energy surfaces or energy landscapes for the two, where each of the states are shown as energy wells, the two native states, and they're called C and O for closed channel and open channel. And the closed channel binds agonist weakly, and the open channel binds agonist strongly. So in the absence of agonists, the open state is less stable than the closed state, so the probability of being open is quite small. But when you add agonists, the situation changes. Open becomes more stable than C. And the reason this happens is because of this difference in affinity. So you add a little bit of stabilizing energy to C, but you add a lot of stabilizing energy to O. And that changes the uphill reaction into a downhill reaction. So this is true of all receptors. Agonists turn on receptors because they bind with higher affinity to the active conformation. I think that's a rule for all receptors now. Now, there's another state in this picture, which is right here, this hump in the middle called the transition state. And in acetylcholine receptors, this state is stabilized to the same extent as the open state. So this mountain that you have to climb to get from closed to open is much smaller when there's ligand on the protein. So the opening rate as well as the open probability goes up. And I think that's going to be true for any receptor that elicits a fast response. So we have to we'll come back to this transition state in great detail later on. So we can take that energy landscape and represent it as the standard way in chemistry as a reaction scheme, where the vertical lines represent the switch between C and O, and the horizontal lines represent binding of ligand. There are two affinities, two equilibrium dissociation constants, but the word affinity is usually applied to the low affinity binding, which is in the main activation sequence. Now, I said there's two acetylcholine binding sites, so there would have to be a second square over here, but we're going to keep things simple and just talk about one site at a time. And again, this is the only rate constant that changes between going from closed to open, from without agonist to with agonist. It's this forward rate because of that transition rate state change. So, no, this is not my postdoc advisor. 1840, Germain Henri S. Was a German guy working in St. Petersburg, and he was a data fiend, and he collected a whole lot of data and came up with an empirical observation, and he formulated a law called Hess's law, which said when you have any two stable species that are connected by different pathways, the energy difference between these species is independent of the pathway. This is before the conservation of energy was well established. Now we would call this the conservation of energy. So what that means is getting across these two states is the same energy as this versus this pathway. This pathway exists, but it's rarely taken. So that means the product of these two equilibrium constants equals the product of these two equilibrium constants, which leads to this green equation here. So the ratio of gating constants is equal to the ratio of equilibrium dissociation constant, and that ratio is called the coupling constant. Now, this is generally accepted to be true, but some people recently have been saying that in ion channels that may not be true. You have this only holds when there's no external energy into the system, and there is external energy into an ion channel system. That is with the energy from the ion flow. There also could be energy from membrane bending or even cellular events, cellular metabolism. So what we set out to do is measure these four equilibrium constants independently using single channel kinetic methods. We were able to open the channel constitutively using mutations and then bind agonists to that in order to get this equilibrium dissociation constant, which is quite difficult to do. And it turns out this equation works. This ratio holds for four different agonists, three different kinds of binding sites. This is correct. Germain Henri Hess's law applies to acetylcholine receptors. There is no significant input of external energy. Everything that happens spontaneously, driven by temperature alone. That is when you're in the C native state, you're thermally driven to move out of it, and you're trying to get to O. And when there's agonists around, agonists do not initiate the motion. They just lower that energy barrier and let you get to O more easily and stay in O. So everything is spontaneous here. There's all thermal, everything's in thermal equilibrium. And I think this is going to be true for, this may or may not be true for other receptors, but you're innocent until proven guilty. It's incumbent upon whoever says that this law is not hold to prove it, to prove that. How's my voice? Is it hanging in there?
You sound good.
No, it's good.
Okay, I don't want to be cutting out. Let's get back to a dose response curve. So we've gone from energy to equilibrium constants. Let's get back to our dose response curve. For our purposes, there's only three things you need to know about a dose response curve: the minimum value, the maximum value, and the midpoint on the x-axis, which is called EC50. So the difference between the minimum and the maximum is called efficacy, but since the minimum is the same, that's the zero concentration asymptote, that's the same for all ligands. Basically, the maximum gives you the efficacy, and the word potency is another word for EC50, which is related to the energy in, but it's not exactly the energy in. So it's possible to calculate all the equilibrium constants from the cycle from these three measurements. So from the maximum, you get the gating equilibrium constant with an agonist. From the minimum, you get the gating equilibrium constant without any agonist. And from the EC50 and the maximum, you get this the low affinity gating equilibrium constant. And then you can just use that green equation to calculate the fourth equilibrium constant. So we can get all four equilibrium constants from these three measurements. Now, minimum is very difficult to measure because it's so small. And but later in the talk, I'm going to give you a very simple way to measure the minimum that should be easily applied. So we have all four equilibrium constants. Let's look at a real dose response curves. This is from a mouse vertebrate neuromuscular nicotinic receptor. ACH is the neurotransmitter. Epibadidine is a frog toxin. Actually, the frogs eats insects and stores the toxin. The insects make the toxin and the frog just stores it. TMA is tetramethylammonium. And we know a priori in this experiment, we know the minimum. We have taken great pains to measure the minimum, and we came up with this number. Believe it or not, this number is extremely important, whether it's 10 to the 7th, 10 to the 8th, 10 to the 9th. It all looks like zero to a physiologist. But for an efficiency person, you need to know this number in order to calculate that KDO using the green equation. So let's go through this. We measure EC50, we fit it to the Hill equation, we get an EC50, we get a maximum, we calculate KDC and KDO. The low affinity binding is in the micromolar range, the high affinity binding is in the nanomolar range. We take the ratio to get the coupling constant, and here they are. These are the coupling constants for these three agonists. And again, the coupling constant tells you how partial your agonist is. ACH is a full agonist, these guys are partial, and you can go all the way down to 1. And when you get to 1, you have a pure antagonist, but it's hard to measure things that are down to 1. Okay, that's my introduction. We now know energy, equilibrium constants, and dose response curves. So let's go talk about efficiency. So efficiency is for any machine, the efficiency is the energy out over energy in. And receptors are machines, they're molecular machines, which means they're subject to Brownian motion, Brownian influences, but nonetheless, they're machines. So in a receptor, efficiency is the fraction of the binding energy, that's the energy in, converted into gating energy, that's the energy out. So what are these values? Well, from the green equation, we know the energy out. The energy out is this ratio here. Energy is minus the log of an equilibrium constant is a ratio. So just taking the log, a negative log of this, the numerator is the energy out. This is the numerator in energy terms. It's proportional to that. And this is eta, by the way, which is the standard thermodynamic symbol for energy, for efficiency. And what's the energy in? Well, the energy in is the maximum energy in. That's the energy coming from the high affinity bond. Now, so you take this, so this is the equation for efficiency, and you just solve that easily, and this is the basic equation. Efficiency is equal to 1 minus the binding energy ratio. I'll derive this a different way later on if you don't like what I just did. So we thought we were very clever when we derived this, but in fact, this was derived 200 years ago. Not my postdoc advisor, Sadie Carnot and Lord Kelvin came up with this equation for a heat engine, for a steam engine, where instead of the binding energy ratio, we just used the temperature ratio, T hot over T cold. So how do you measure efficiency? Well, one way to do it is just by getting a bucket of protein in the C conformation, adding agonists, make sure that the protein stays C when you bind it, that you're measuring C, and get the KD and take the log. Do the same thing for O, get an O protein, high affinity state, and measure it. And I think take the log and calculate efficiency. And I think this is the future. This is, I think, how it's going to be done if people want to do this in the future. That's not, and if anybody wants to collaborate on this, I'm happy to collaborate with the ACH receptors to test the idea that you can do it this way. But I told you we can get there from kinetic modeling and from a dose. I showed you how you get there from a dose response curve. So let's stick with those two methods. The rest of the talk, I'm going to measure efficiency by those two methods. So here's our dose response curve. And now looking at it with an eye towards efficiency, you can see that the energy in is about the same for ACH and epibadidine, but ACH has a higher response. So you would say ACH is the more efficient agonist. And sure enough, what about ACH and TMA? I don't know. Well, let's do the numbers. Here are those KDs. Does anybody know the log of 174 micromolar divided by the log of 30 nanomolar? It's exactly 0.5. I don't know if my picture is covering up the 50%. This is 50% up here for ACH, 42% and 54%. So for any dose response curve, for any agonist on any receptor, you can get an efficiency number just by doing the analysis I just showed. So ACH is more efficient than epibadidine, and TMA turns out to be more efficient than ACH. So what's interesting about this is I don't think this has ever been done before, and this is something that could have been done 50 years ago. As soon as ACH receptors were identified as allosteric proteins by Arthur Carlin and Jean-Pierre Changeau, that this, at least in theory, this could have been done, and it wasn't done for 50 years. It took a while to get the measurements. You had to measure the minimum. That was the hard part. So this is really old school stuff that there's nothing new under the sun here. But I don't think anybody ever measured efficiency. But this is not why. So it's useful to have a quantitative number of efficiency, but that's not why efficiency is useful. The reason why efficiency is useful is because of this. Many agonists have the same efficiency. This is my graduate student, not my postdoc advisor. Snail JD in 2012 measured KDC and calculated KDO for 7 different agonists using from dose response curves, and found this remarkable relationship that for all of these agonists, binding energy approximately doubled when the protein spontaneously moved from C to O. So a protein in C was half the binding energy to the protein in O. So the slope of this line is log KDC divided by log KDO, which is efficiency. So all of these agonists have the same efficiency. We didn't know about efficiency at the time we made this observation. And this holds for very weak agonists, which have a very low efficacy compared to high efficacy, from low affinity to high affinity over several orders of magnitude. They all have the same efficiency. And this puzzled us. This threw us for a loop, because we knew that the binding energy was going to be greater to O than to C, but we did not know that it was going to be double for this whole series here. So this was a surprise. And we didn't know what this meant for many years. And it wasn't until I had Thanksgiving dinner with my son, who was an engineer, who told me, hey, an energy ratio is efficiency. So that's when I started to work on efficiency. But before we get to understanding this curve, I want to it affords a new kind of analysis, another level of analysis where I think is important and useful. And that is an efficiency plot. So if you combine the green and the pink equations, you get this blue equation, which is a straight line, y equal mx plus b, where y is the log of the gating equilibrium constant and x is the log of the binding equilibrium constant. And if you take the data for now 9 different agonists plotted on individual binding sites, you see that they all fall on a straight line, and the straight line has a slope m, which is related to efficiency and the number of binding sites. That's all that goes into the slope n. So it's very easy to get efficiency when you plot your data this way. And the interesting thing here is the y-intercept of this equation is log L0. So this, you don't need to know minimum to get efficiency. You just need to know maximum and EC50 in order to get this line. So if you have a family of agonists that have the same efficiency, they're going to fall on a straight line. So all of these agonists have the same efficiency. And what you note is the same efficiency applies to agonists having different scaffolds. The structure of ACH is different than that of nicotine, and DNPP is quite different. Anabasine, nornicotine, carbachol, these all are related to those up there. But you cannot use the chemistry of these guys to predict what the efficiency is. They all have the same efficiency. And so for this group of agonists, efficacy and affinity are correlated over wide ranges. So this is 2 orders of magnitude in affinity, 4 orders of magnitude in efficacy. This is a plot of energy in, energy out. This is affinity, this is efficacy. Log affinity, log efficacy is what we're plotting here. And for all this wide range of values, they have the same efficiency. Efficiency is something different. It is not efficacy, it is not affinity, it is the correlation between the two. And I just want to let you know that each one of these points is an entire dose response curve. So this is the correlation between energy in, energy out for that agonist, determined from everything in the dose response curve, from the maximum EC50 and minimum. Maximum and EC50. Okay, so we did this for 20 different ligands. This was 9. This was the first 9. Here are the next 10, which we found many of them follow along the same line with 42%, which is what epibadidine was up here. And these guys, some of them resembled epibadidine. They have this bridge nitrogen, azabicycloheptane, anatoxin, epiboxidine, cytosine, smoking cessation drug. But some of them didn't. This is tetraethyl ammonium, and this is tetramethylphosphonium. There's not even a nitrogen in the thing. And it has the same efficiency as epibadidine. And 3 of them fell on this line with TMA with a 54% efficiency. Now, there's 2 points to make. I'll make the second point first. These 3 lines were fitted independently to a straight line, and they all gave the same L0. So we did not assume L0. We didn't. And the L0 that we get when we go over to find what it is the same L0 as we got by doing the horrendous set of experiments that we did for 10 years at the early part of this, in the 2010s. We spent a lot of effort getting L0. This is a very easy way to get L0. This comes directly from dose response curves, from the maximum and the EC50. You don't need to know L0. You get efficiency and you get L0. So this is why I recommend this analysis, because you're going to need to know L0. Second point I want to make is that the efficiency values are discrete and precise. So we took, they're not scattered all over the place. They fall, we have 19 ligands here, and they fall on one of 3 lines. They're not like scattered all over the place. And the error limits are really tight on this. It took us a while to realize that 54 and 51% represent 2 different classes, but they do, and I'll give you supporting evidence for that later in the talk. So I gave you 19. There's a 20th. Here's the 20th. It's varenicline. It's also known as Chantrix. It's a smoking cessation drug that's on the market. And we tried to find more varenicline analogs online, but we couldn't. We didn't know we couldn't get a hold of them. We didn't see any for sale, or we didn't know anybody who had any. So we only have one that looks like this. And using the same L0 as the others, which of course L0 is the same for all, we get 35% for that one. So what I want to make point here is the correlation between efficacy and affinity is apparent only when you segregate agonists according to efficiency. So if you threw all these together, if you just took randomly 5 or 6 of these things, if you did 5 or 6 dose response curves of agonists, you would come to the conclusion that there is no correlation between affinity and efficacy. So here you see 3 ligands that have the same affinity but very different efficacies. Here's 3 ligands that have the same efficacy but very different affinities. So it's only when you have a lot of data and you see these correlations that exist between families of agonists. So agonists can be classified according to efficiency. When an agonist is an agonist, it's an agonist. No. You have to be able to understand your different agonists belong to different families, and that's when you see the correlation between affinity and efficacy. So does this happen in other receptors? Well, maybe. We didn't do these experiments. We went to the literature and found what we thought were the best examples of experiments where people measured the binding energy and the gating energy, or the activation energy. So this is from Trevor Smart's lab. Who did a very thorough analysis of GABA receptors. But what we did is we used statistical methods to identify outliers in each of these plots. So the red ones are the outliers, and we just fit the blue ones. And you can see we got an efficiency of 39% to 60% for these different, which is in the range of the ACH receptors that we see 35 to 54% for the ACH receptor. So and we also got the intercepts to give you L zeros for these, which are on the range of 10 to the 4, -4 to 10 to -6. So it would all look like zero current. And there is evidence that the GABA receptor, the direct evidence that this is correct, the 10 to -3 is correct. So I think it does apply to other receptors. And now the muscarinic receptors is particularly interested because they in the paper used this as an example of saying that there's no correlation between affinity and efficacy. I would tend to say these two outliers belong to a different efficiency group. Maybe a 25% or 30% efficiency group, maybe 35% efficiency group. These two are pilocarpine and oxytremerine, and the rest of these are more like ACH and carbachol. So we can talk about that in a question period. This is a GPCR, so we're not coupling the conformational change directly to ion flow. It's being coupled through G proteins to potassium channels. So it's a more indirect coupling, but we still get an efficiency estimate. All right, let's get back to ACH receptors. It looked to us, just by inspection, that the efficiency changed with the volume of the agonist. So we calculated the volume of the head group, and that's a little bit tricky calculation because you don't know where the head group, exactly where it ends. But we see there is this correlation. So size matters. The bigger the agonist, the smaller the efficiency, although it's not a great relationship. There's something more complicated than size going on, but size seems to be one determinant of what determines efficiency. Now we like this fit nicely with some previous studies we did of the binding site. So this is a picture of the alpha-3 beta-4 binding site from Ryan Hibbs's lab showing nicotine, and this nitrogen in nicotine is surrounded by 5 aromatics. This is the well-known aromatic cage of nicotinic receptors. So we measured a bunch of parameters of this geometric parameters of this binding site, one of which was the volume of the cage, volume of the pyramid formed by connecting the centroids of these 5 ligands. And I'm going to show you some data later on about a glycine, a very important glycine that sits up here. So what we observed, what we did is we made homology models of closed and open receptor, closed and open binding sites. We did MD ligands, did short MD formulations just to equilibrate the thing, and we measured the volumes of the pockets. Now we're doing this now with PDB files as opposed to homology models, but we're getting the same results. What we found was that the closed pyramid has a larger volume than the open pyramid. I don't know if this has been observed since, but at the time we did this, I think we were the first to observe this. So it's about a 25% reduction in volume when the binding site goes from closed to open with acetylcholine, and when epibatidine is in the binding site, the starting point is about the same, but the reduction in the binding in the volume is less with epibatidine. And this is the results for 4 different agonists and on 2 different binding sites. For the 51% agonist, the efficiency agonist, they both start at the same. This is now the cavity volume. But when the channel goes to O, when it's in the O state, this is the percent contraction. There's about a 25% contraction for the high efficiency agonist and only about a 12% contraction. So the contraction is less when there's low efficiency agonists. So why do a larger agonist have low efficiencies? This is our hypothesis. We haven't tested it yet. In C to O, a contraction of the cavity is limited by van der Waals contacts with the agonist. That is, there's steric bumping with the agonist. And this in turn limits the energy transfer. It's the contraction of the pocket is somehow correlated with energy transfer to the rest of the gating machining. So the limiting of the pocket contracture limits the energy transfer to the next steps in the gating process. That's our hypothesis. That can be tested through molecular dynamic simulations. So what else do we know? We know that efficiency depends on the composition of the binding site. We made 45 different mutations of those aromatics and other residues, and G153 at the binding site. And we measured the efficiency. Now for this, we had to measure L0 for all 45 of these. So this is a lot of data that is going into this. So for each one, we had to do a dose response curve, which measured the L0. So there's a lot of data in this. So most of the aromatic mutations didn't do anything. So this is ACH efficiency, which started at 51, and we end up at 51. But some of them increased the efficiency, mostly those at 149, increased the efficiency to 55%, and one of them, 190A, decreased the efficiency to 35%. And when we did this for the 153 mutations, what we did is there were 4 different mutations and used 4 different agonists. One of the mutations is G153S, which causes the congenital myasthenic mutation. So these are all either 55 or 51% efficiency agonists. They all reduced the number. They all reduced it to 42%, and except for this one, which was 32%. So we know these numbers. We should know these numbers by now. 51, 55, 42, 35. We've seen these before. These are the 4 different categories that we defined on a wild type. So when you make all these mutants, you're not jumping to some intermediate, you're not going to 70% or 38% or 25%. You're jumping to one of the ones that exists in wild type receptors. So efficiency values are not only discrete and precise, they're also modal. So I think that efficiency, the pattern of efficiencies that you see in a binding site is like a spectrum. It's like, maybe a barcode. It's the spectrum of the binding site, because you get discrete lines at efficiencies, and that the hypothesis that the binding sites adopt discrete structures that correlate with efficiency. That is, the binding site, when it goes from big to small, it's not gooey. It doesn't just go anywhere. There's no induced fit. It is trying to get to a discrete structure that's available to it. And with a high efficiency ligand, it goes to a compact site. But when you have something like epibadidine or tetramethylammonium in there that blocks the contraction, you go to an alternative structure which is not as compact, but is discrete. It is a discrete structure, and I think structural biologists should be looking for this. I hope they find it. A little more speculatively, it looks like to me that mutations that change efficiency mark the conformational change pathway. So 198 doesn't do anything to efficiency. I don't think 198 is involved in getting energy out of the binding pocket. 149 actually increases efficiency. That means when you put an A there, you don't have to move that bulky tryptophan around. And 198A reduces it to the 35, the same as varenicline. So I think that these 2 guys are involved in moving energy out of the binding pocket. 93 is sort of split between 51 and 55, depending on which side chain it's there. But we're now trying to expand our radius around the binding site, looking for residues that are in the outer parts of the binding site, further away. And then we're hoping that we can we're hoping that efficiency marks the conformational change pathway, although that needs to be determined. Okay, enough about ACH receptor binding sites. Let's talk about what efficiency is good for. One thing it can be used for is to simplify and extend dose response analysis from those 2 green and from the green and pink equations. That if you know N and you know L0, if you know N and you know L0, then you can use efficacy to compute affinity and affinity to compute efficacy. You can use L2 to compute KD, and from KD you can compute L2. Now it doesn't save you any free parameters because you need to know efficiency. But I think efficiency is going to be able to be estimated from structure. So if you take a nicotine and you put a fluoride on it, or you make a chloride on a DMP, it's still going to be 51% efficiency, but it could have very different affinities and efficacy. So if you're scanning a library of compounds based on the size of the molecule and the other molecules that have been measured, I think you have a pretty good guess at what the efficiency is. And of course, L0, once you measure it once, you're done. So L0 is going to be known for every receptor sooner or later. So once you know L0 and you can guess at efficiency from structure, so that is when this thing becomes useful. Or maybe you need to structure the binding site too. But in any case, here's what we did. We have these dose response curve. I've added carbachol to the mix here. These are now whole cell currents measured in an ion flux machine. So this, you don't need single channels to do all this. You can take just the highest concentration, just these points here. We know the efficiencies of 54, 51, and 42. We know those efficiencies. We can calculate the following dose response curves. I think we use 50% for these guys, not 54. For all three of these guys, we use 50%. But you can see, you can calculate reasonably well from just one EC50 can be estimated from the response to just one agonist concentration. This has got to be useful at some point. You don't need to go scanning all the whole curve. You just measure these 1 points here, no efficiency, you can calculate the whole curve. And similarly, we can do this from a lot of people. A lot of people normalize their curves because they don't know how many channels are in the patch. So this is a normalized dose response curve for the 4 agonists that I showed before. Now we've taken just the EC50s, these concentrations here, and we use from EC50, we can regain the efficacy information given N and L0. So these are the curves that we calculate. Now this is using 50% for TMA, and this is using 55% for TNA for efficiency. So this is further evidence that efficiency values are really precise. In fact, this is probably a good way. This could be a way to estimate efficiency. If I fit this with efficiency as a free parameter, I would get 55% for efficiency. So efficacy information recover from a normalized CRC. This seems magical to me that you can take this and you can go back in the literature, take literature plots where you have normalized dose response curves. And if you know these two parameters, you can unnormalize them and get efficacy information. Seems to me that's going to be interesting at some point. Okay, now I'm going to go to the third part of the talk, where it's going to get a little complicated. Why do agonists with very different affinities and efficacies have the same efficiency? Why were all those agonists fall on the same line? To that, I need to introduce 2 more pieces of data, 2 more results. One result is the agonist binding process is not simple. Well, what we did is in that original measurements of the equilibrium constants, we actually measured the rate constants, the forward and the backward rate constants for all 4 of those steps in the cycle to one binding site at a time for 4 different agonists, or in one binding site it was 8 different agonists. And these are the results. So the main result is that agonist had to do with agonist association. The forward rate constant of the agonist getting into the binding site is slow, much slower than diffusion. This is ACH, and is agonist dependent. It drops all the way down to 10 to the 6 per second, which is 4 orders of magnitude lower than diffusion. So it's slow and agonist dependent getting into C. The difference was getting into O, which is the smaller binding pocket, is roughly at the diffusional limits. Maybe not for C, but in all cases, it's for choline, but in all cases, it's faster than getting into C. It gets into O faster than the C. The high affinity of O is due largely to a fast on rate. Now, this is the off rate here, and it is slower. The off rate is slower, but it's the on rate that is predominantly responsible for the high affinity of O. You can see that for getting out of C is about the same for these 4 agonists. So this was not a complete supply because Claudio Grossman had done a different kind of experiment, which was much more indirect, but came up with the same result, that getting into O is faster than getting into C. So this suggests to us there's a conformational change for the agonist required for the agonist to get into the C state that's not required to get into the O state. So let's see what this also reflects on some common conceptions about binding. If you ask many people about binding, and they would say agonists diffuse into the target site. I've seen this written in papers, even papers by very fancy people working on nicotinic receptors. They start their paper by saying ACH diffuses into the target site. Well, that's not true. Definitely not true to C, possibly to O. So the diffusion we've given here is 4 times 10 to the ninth. And some of these guys don't have any rotors, so it's not like you're waiting for the ligand to fold up into the right state. This is TMA, which is symmetrical. And all these guys, this guy has, if anything, these all have the same diffusion constant. Maybe TMA, if anything, is going to be faster than ACH, but they're all approximately the same diffusion constant. So it's not diffusion into the site, there's a conformational change. The high affinity O is caused by a steric barrier. People like to think of a lid, a loop coming over and capping over the binding site, or a clamshell motion, or something trapping the ligand in the binding site. So it's true that open site is smaller than the big site, but it can't be a lid because K-on is faster than to C. If it's a lid, then getting in is going to be slower. So people have known this, and they ignore this result. And this is a very robust result. This happened at 3 different binding sites with 8 different agonists. So this is a very robust result. So it's not a steric. In fact, there's a barrier getting there's a barrier to getting into C, not to O. We don't know if it's a steric barrier. It could be as little as a rotation of a charged molecule put in the pathway for binding. But the barrier is to getting into C. It is not a steric barrier. It's causing high affinity. And it's possible to compute affinity by docking. People dock billions of compounds and measure the stability of the dock state and say that has something to do with affinity. Well, that may be true for some ligands and some receptors, but it's not going to be true for ACH receptors, GABA receptors, and glutamate receptors, which all show this subdiffusional agonist-dependent binding to C. And so affinity is set by K-on. K-off is the same, it's K-on, and when you do docking, all you're going to get is K-off. So it's not going to be useful for these receptors and these small agonists, and maybe other receptors and bigger agonists that would be useful. Okay, that's the first point. The second point is there are undetected intermediate states. So 1913, Michaelis-Menten, stick an ES in there, revolutionizing and upsetting the apple cart of enzyme kinetics. And they proposed this in 1913, but it was not confirmed experimentally till 1943 when Britton Chance invented the stop flow apparatus and saw a spectroscopic signal for this in a peroxidase enzyme. Not my postdoc members. Yes, this is my postdoctoral medal, Jose Del Castillo. So in 1955, Del Castillo, who was then a postdoc of the great Bernard Katz, took a page from Michaelis-Menten. It took a long time to take that page, but they eventually did it. They stuck an AC state in between C and O, and it was confirmed in 1985. This is after Nair and Sockman invented the patch clamp, and Cahoon and Sockman measured this, got a signal from this state right here. So we're going to continue along these lines now in the next couple of slides, and we're going to break these states, binding and gating, we're going to break those into intermediate states. And as Dennis Doherty once told me, there always are undetected intermediate states down to the quantum level. So you can slice and dice these arrows as finely as you care to. So we're going to now dice these 2 guys up. So we'll talk about binding and gating. Binding, I said, has two, I suggest it has 2 components. One is the diffusional component, and the second component is the KDC. Now, this is the part of KDC that changes between agonists. They all have a constant energy offset from diffusion that's about the same for all. So this, I'm not saying overall KDC requires both of these. This is the delta KDC when you're making a comparison between agonists. So that's the blue color. And in gating, I'll show you later, we think there are 1, 2, 3, 4 intermediate states in gating. The first of which involves a change in the binding sock that determines the coupling constant. Again, it's a change in the coupling constant. All these events are energy offsets that get added to the gray bars are energy offsets that are the same for all agonists. It's just the 2 colored ones are the ones that determine affinity and efficacy. So I'm going to call this conformational event that catch. This is the one that removes the barrier. I have no idea what the barrier is. It lets the agonist enter the binding pocket to bind with low affinity. So binding now can be replaced by catch, and catch determines affinity. Hold, the pocket contracts. I think that's true. Binding energy increases, coupling constant, to determine efficacy. So gating, I'm going to try to get rid of the words binding and gating here because I think they're confusing people. Catch and hold are what's happening. Catch is the event that causes affinity, and hold is the event that causes efficacy. I'm naming the event, not the state. So this is the transition state, not the state. Okay, so why do agonists with very different affinities and efficacies have the same efficiency? This is the idea because catch and hold are parts of a single energy-linked set of rearrangements. There's a linear free energy relationship between the catch and the hold conformational events. So I'm now going to show the potential energy surface, the energy landscape, just for the two agonist-dependent stuff. What precedes is the same for all agonists, and what follows is agonist-independent. These are the parts that determine the dose-response curve. So this is the energy landscape for catch and hold, and I have these tethered together. So whatever happens to catch happens to hold according to this tilt. So the energy change in catch, as we know, log KDC, plus the offset from diffusion. The energy change in hold is the difference between the two, the numerator of the efficiency term. So the sum of the two is log KDO. So we now have efficiency as being the part of this energy landscape that goes towards gating. That's hold. That's this number divided by that number, which gives us our efficiency equation. This is the alternative derivation of efficiency. And the key is that they're always tethered together. So if you have an agonist that is weak, that has less total energy, KDO is smaller, you're going to still tilt them. They're still going to be tethered together. So the ratio of binding energies, the ratio of the hold energy relative to the total energy is going to be the same. So you're going to get the same efficiency because the ratio of the energies stays the same for weak and strong agonists. So it doesn't matter the affinity of the agonist, it doesn't matter the efficacy of the agonist. What matters is the ratio, and the ratio is the same because these two follow a free energy relationship. Just to say what I mean by that a little bit, so once there's crosstalk.
Tony, you're buzzed out, or your mic is out. Okay, it's better.
I think I'm covering something up with my hands. Okay, so when you when the agonist arrives and you undergo the catch conformational change, it lowers the transition state and endpoint for the hold conformational change. So that's why you have this thing tethered together. That's what I mean by a linear free energy relationship. Whatever structural change happens in catch primes the system, or I don't want to use the word prime, it lowers the transition state for the next step of the gating reaction, which is hold. So catch lowers the transition state to hold, and so on down the chain. So that's what I mean by the catch and hold linear free energy relationship being the underlying basis for efficiency. So now I'm going to continue now about the rest of the conformational wave, and the next two slides are going to go off the deep end here because I have to go to this slide here, which is our gating conformational wave, which comes from 5-value analysis. We measured about 1,000 different mutations, and we measured the effect of the mutations on the transition state and the end state, and that ratio of those changes in energy gives you a value called phi. And this is the distribution of phi values, which I'm not going to go through this, but phi relates to the position in a sequential reaction chain of where the mutated residue changes its energy. So if we have a phi of 0.9, that means it happened at the beginning, and a phi of 0.8 means it happened a little bit later, phi of 0.6 somewhere in the middle, phi of 0.3 towards the end, and a phi of 0 is at the very end of this chain of reaction. There's a theory that we worked out that relates phi values to position in the reaction sequence. And what's great about phi is because we're mutating residues, we can pinpoint the location of these energy changes. So it turns out all the green guys, the early guys, are at the binding site. Those are the ones that do hold. These guys here, the red guys are in the extracellular domain. The yellow guys are in the transmembrane domain. The orange guys are around the gate, and the blue guys, of which were hard to measure, are right at the gate, at the 9' position in M2. So we have structural information from phi. We can get a structural map, and I've named each of these because people like to name things. They've named each of these transitions. So this is the hold transition. This is all inside of gating now. The hold is followed by twist, tilt, rip, and pop, and these things from the binding site, the extracellular domain, transmembrane domain, gate, and water at the gate. They're associated with different structural elements. I have a movie of this if you want to see a movie later on. But I expect it took 30 years for McAllis Amendment to be confirmed. It took 40 years, I think. And it took 30 years for Del Castillo and Katz to be confirmed. It's going to take 40 years for this to be confirmed. But we're halfway there. I proposed this sometime around 2010. So recently there's been a detection of a very fast event called flip. And it's a glitch of about 5 microseconds that probably represents something happening in this transition state. And we think phi is a much better way to measure the structure of the transition state rather than direct detection. So flip is, however, it gives you time information, which phi does not. So a 5 microsecond event suggests that these transitions are on the order of 100 nanoseconds each. So the system undergoes Brownian motion across this top, and when you go from O to the flip state, you're probably just in the early stages of the closure. You probably don't make it all the way back to hold. But it's good to know that flip is it's not a flop. Flip is useful. So in the final slide, I want to put forth the hypothesis that everything between agonist diffusion and ion flow is linked. And when I say linked, I mean linked through linear free energy relationships and linked structurally. So these energy is structure. So if you have an energy relationship, then you have a structural relationship. I think the structure guys should be looking for these relationships. So here's our low resolution recording where you have an energy landscape without agonists, and here's an energy landscape with agonists, and it goes from uphill to downhill. That was in the very first slide in this potential energy surface. This is what I think the landscape looks like when we take into account all these events. So now I've written the states in between the events, the transition states. And the idea here is, so this bumpy road, uphill road, is what we would see as this in low bandwidth recordings. If you had a 100 nanosecond event, you would see this. If you have a microsecond event, you'd see one little bip in here. If you had a 100 nanosecond instrument, you would see these 5 little events. And these 5 events come together to form this energy barrier here. And this is what you'd see with agonists. The thing is tilted down, you would see this energy landscape because these 5 together, but if you could see it, you could see that. And the idea is this, that when an agonist shows up at the binding site, it lowers the transition state. An agonist is like a catalyst that resembles the transition state for the catch conformational change. So when an agonist shows up, it lowers the transition state and the end state of the catch conformational change, which then lowers the hold, which then lowers the twist, then lowers the tilt, rip, pop. So what I imagine here is a whole series of potential energy surfaces that as this system proceeds, it proceeds downhill through all these linear for energy relationships. It's like a zipper. This thing, you zip it up from here. This thing gets zipped down to here because the agonist triggers that zipper. And this happened, and I also think that this is a obligatory zipper. That when you add a mutation that causes the channel to be spontaneously open and pull this thing down, you then pull down all the intermediate states until you get to catch. You go all the way back and pull down catch, and that's why O is diffusional. Because when the O state, which has been made to be active that's why O is faster than to C, because catch has already happened. You make the channel open by a mutation far away down in the transmembrane domain, and it forces all the way back. All these things go backwards until you've lowered catch. So agonists enforce fast opening by lowering catch, and mutations that cause constitutive opening enforce fast binding because they lower catch. So that's my hypothesis, and I don't know if we want to call it the zipper model. I'm not sure what to call it. So I'm going to end now by giving a quick summary. Like affinity and efficacy, efficiency is a general property that pertains to any agonist of any receptor. It is a fundamental attribute of agonists that I think should be investigated in many different receptors. Groups of agonists can be classified by efficiency. That's very important too. That's in ACH receptors, and it looks like it's also true in other receptors. And I recommend using an efficiency plot because you get L0 as part of the bargain. Catch, hold, and maybe everything else is linked energetically and structurally. I'll skip the ACH ones. Well, modal precise, that's the barcode, agonist size, binding site contraction, and binding site composition. Those are those data. And I want to just mention that it's possible, yes, it may apply to other receptors. It's possible it will be useful in dose response analysis. If you're screening drugs and you only have to measure one concentration, mazel tov, that's a good thing. It can be predicted from structure alone, maybe. That needs to be determined. These are possibilities. It marks the pathway of possible change, maybe. And it's the basis for allosteric modulators in disease. I said I wasn't going to talk about diseases, but we did have one mutation, which was the congenital myasthenic mutant, which resulted in a 20% reduction in the efficiency of ACH. So maybe that's what's causing the disease. I don't know. We have to look at, I think Richard Webster in Oxford is going to be looking at other congenital myasthenic mutants and see if they cause disease. So here's my thank yous. These are the people that have worked in my lab over the years and worked on the ACH receptor and other receptors as well. The people in bold are the people who were most intimately working on the efficiency prospect. I want to thank particularly John Richard for helping with linear for energies, and Rob Colson for suggesting that general tilt of the as a cause for the correlation, and Andy Harris for getting me to think hard about what's happening in catch and hold. Pablo Paez let us use his ion flux machine, and of course these three physics guys were always there to help. Jan Jordan has been a stalwart of the lab for my whole career here, and NIH has been very good to me, although they don't like efficiency. I've tried 3 times; they don't like efficiency. I don't know, so I'll keep trying because I think it's very important. And finally, I want to thank the main star of the show, which is the acetylcholine receptor. This is the best prep ever. Anybody who's ever worked on this knows how good it is. It just reveals its secrets to you. It lets you get down to the bottom of the ocean like no other receptor. You can go deep, deep, deep. And I think, and I hope you would agree that after the concept of receptor affinity and efficacy, maybe efficiency belongs on this list. And then I thank you. That's the end. Is anybody
Tony?
still there?
As usual, we got a lot of people today, so I'll just quickly break it open to the students first. If you have any questions, grad students, postdocs, and then we'll open it up to everybody. So if you want to raise your hand with the reactions, if you have any questions.
Say something if you have a question, because all I
Or
can
say something.
Yeah.
Okay, then. Well,
Thank you, Carl.
anyone else has any other questions? We can start questions from everyone then. Go ahead.
You can request
Hi,
to see
Tony.
a movie if you want. I have a movie if you want to see a gating movie.
So really nice talk. I think that's really cool stuff. I got a question about this idea of modal structures or modal conformations of the binding pocket. Do you have any ideas about, what that might be?
No, I'm not a structure person. And my little experience that I have with structure is I don't want to be a structure person. So I don't know what it is. The idea is that those configuration of 5 aromatic residues can take on specific preferred conformations. There are pre-existing conformations that are favored. It wants to take on with ACH, it takes on the most compact of those. But when you have other bigger ligands, the compaction can't happen because of steric bumping, and the configuration of those 5 takes an alternative form. But it's not some general form that depends on the agonist, because it depends on the agonist efficiency as the character. It doesn't depend on the agonist affinity or efficacy. It's not like a rubber room in there where you can do induced fit or whatever the word they use now. But I don't know what it is structurally. I think this is a question for MD and structure, and I think most of what I said is going to be resolved eventually through MD and structure. Energy always gets there first, structure gets there accurately. So I don't know what, does that answer your question?
Yeah.
But I do think that those efficiencies give you a spectrum, and I think if you have a different binding site, like the adult type, like the fetal type binding site, or a GABA receptor binding site, or an NMDA receptor binding site, or whatever binding site it is, or the muscarinic receptor binding site, which looks a lot like the ACH one, is going to have the same spectrum of efficiencies, because binding sites can only take on a limited number of active conformations.
Tony, can you hear me?
Yeah.
Yeah, can you define efficiency in 1 or 2 sentences for the choline receptor? I mean, it's for a motor, for an engine, isn't efficiency the amount of energy used to do work or something, or the fraction of the total energy is used to do work?
Useful energy out over the total energy in. So it's the fraction of binding energy that's converted into conformational energy. It's a chemical mechanical conversion between chemical energy and the mechanical energy of the conformational change. If you're a physicist, you might call it potential energy to kinetic energy, but but I'll stick with binding and gating.
So you can measure total binding energy easily enough. How do you measure binding energy that's used to do work?
I just measure binding energy by that in that landscape. Let me see if I can get that landscape. Yes, I measure binding energy is the catch energy. There's a diffusional component, and then there's this conformational change component that is log KDC. It's probably a delta. There's probably a delta delta G here in energy, and I'm just doing it as energy. So I think I may be cheating here. But this is the binding energy, is the total binding energy, is the energy that you get from getting into the binding site plus the energy you get when you go from low to high affinity, which is the same as the open, the high affinity energy. The total
KD0.
Yeah, KD00 for open.
KDO.
That's the total binding energy, and that's divided into energy for catch and divided into energy for hold. And the position of this on this axis, just like phi is the position of this axis with the transition state, the position of this axis on here is equal to this ratio here. We call this kappa, the log KDC over log KDO. That's what this position is. So this is just like phi value analysis. So if you took a transition state and pulled it down, it's exactly the same as phi value analysis or phi value analysis, right?
All right, well, you can think of binding energy as, well, there's a certain amount of energy expressed just in the binding constant. But then the difference between that and the total binding energy would be the binding energy of the ligand for the open form. Is that right?
That's the binding energy of the ligand from the open form.
Is KD0 just the amount expressed in the observed dissociation constant? I mean, so you get some, I mean, you get right, okay.
This is KDO, not 0. This is KD open.
Okay.
This is the high affinity, KD high affinity.
I think I see. Yeah.
Okay.
Thank
It's
you.
just like phi value analysis, but for a stable state instead of a transition state.
Okay.
That's where we got this whole thing from. It's from phi value analysis.
Tony, Leonislav has had his hand up.
Yeah. So Tony, so this is like extreme conformational selection, right? Your segregation of values of efficiency will indicate that there is like a set of conformations of the binding pocket that are fixed, no?
Yes.
And then just the agonist is just like selecting from those, but there is not a lot of flexibility in those conformations.
Yes, that's what I would say. That there's they're very precise. If you look at these lines, they're very precise. So we don't know about varenicline, but these guys are very tight. 54 and 51% are different. So we would say that the target site of it starts at the same, the resting site is the same, and after catch, we don't know what the conformational change is. But we think that once the ligand's in the binding pocket, it's the target site to which it goes to when it's happened to go to O is conformational selecting. Yes, it's selecting between it only has a few options available to it. It's not like it can do anything it wants. It wants to go to certain targets. Of course, we need to measure more agonists. This is only 20, and each point is a dose response curve. So you need to get more data to see. There could be a 20%, there could be a 60%. By the way, the efficiency of calcium on a BK channel is 63%. So it's in the same range. But yes, I think it is conformational selection.
Okay, and just one last thing. Have you estimated the actual differences in sizes of the pockets in these 3 or 4 lines?
No, just between 51 and 42. And we're doing that now. We've done 51 and 42 here. We can see differences in sizes here. It depends on how you measure. We're using standard software called Hole to get this, and this comes from our funky method of connecting all the rings into form a pyramid, measuring the volume of the pyramid. So it starts at about 120 cubic angstroms when you do the pyramid method, and it drops down by 10% when you have the 42% agonist, 4 different ones, and it drops down by 25%. So you can, I don't know the number, but just reduce this by 25%, and that's the volume of the open state, and this is the volume afterwards. We haven't done a great detail analysis of what exactly the geometry, what is exactly changing. We measured 13 different things, but we don't know exactly what the structure is, and I think that needs to be done by someone who's a better MD person than me. So we're leaving that alone. I don't know if Marco Cecchini's out there, but he'd be the guy to look at this. So that's what you're asking, right? Is what is the structure of those alternate states?
Yeah, right. It's like I was just trying to figure out if it will be something that a structure will pick up easily, right? Like it looks like it's substantial, so it might be easy for, yeah.
Yeah, these differences that we see in the homology models are also apparent in the new PDB files for ACH receptors that have been coming out.
Yeah, okay.
That's where these come from here, not from the homology models. But the trend is the same with that. And these use the whole program gives a much bigger volume for the cavity because it extends. It does a search for water, probes the water volume, and you get a much bigger binding cavity measurement than we got for our little aromatic pocket. So
right,
yeah,
cool, very nice.
Yeah.
Hey, Tony, there's a good.
Can I ask a question here?
And then there's a question in the chat, Tony. I can ask you that afterwards.
Oh,
yeah.
Yes, Fung, go ahead.
Okay, Tony, I think you mentioned the groups of agonists with the same or similar efficiency, right?
Yeah, that's the main observation.
Yes. So mechanistically, I mean, we talk about this. On the whole way, mechanistically, the allosteric model has 3 parameters: the binding, the binding constant, the coupling, allosteric coupling strength, and then the L naught is shown here, the intrinsic. What do you call it? The intrinsic opening, equilibrium opening.
Right.
So mechanistically, I would think that the binding constant and L naught, the intrinsic opening, are more fundamental parameters. Those 2 steps, right?
I agree. And the coupling constant.
And
I would
it's
say
true.
efficiency is fundamental. I'd say L naught, binding constant, and efficiency. Efficiency.
Well, we can argue on this. I mean, in my opinion, that's derived from those two. But that's not the point. My point is that these different agonists must have different affinities, the KDC,
Sure.
and have different L naught, right?
No, L naught is the same. That's the receptor.
Okay, the L naught is the same, and the KDC is different.
Correct.
But then how do you get the same efficiency? Something.
Efficiency is the correlation between L2, the coupling constant, and L naught, if you want to put it that way, and the binding. There's a
No, I'm sorry.
correlation.
I missed the one thing here. The other thing missing here is the allosteric, the coupling strength, C constant.
Well,
So-
I don't do C. I do independently KDC and KDO.
My question is, so these agonists presumably have different binding constant and different allosteric coupling strengths, just like a car. So they have different engines and they have different transmission, but somehow in the magic after assembly, you get the same efficiency. That tells something seems to be more fundamental here. Do you agree?
There's something
What's your
fundamental here.
insight?
I think efficiency is very fundamental. And
No. Well, yeah, okay, you can say, but what I
Fine.
mean is that the binding step is different.
that's the
The
axis.
allosteric coupling strength is also different.
Yes, that's this axis.
Right. So just like in a car, the engine is different, the transmission different, but when you put them together, you got the same efficiency.
Right. But there are families of efficiency. Not all agonists have the same efficiency.
Yeah, well, even within the subgroup, but you do have a group. Those agonists that have different KDC and presumably different coupling strengths. What makes I can't.
I think we should talk about this together in the hallway again.
Okay.
Yeah.
Yeah, something seems to be more fundamental.
Well, I'd be happy to hear it. Fundamental is good.
Okay, there's a question in the chat says, how sensitive are the estimated efficiency values to typical experimental error and variability in EC50 and K estimates?
That's
So
a
how are
very,
your-
that's
your
a very good question. It's very insensitive. They're very robust. You can get a 10% error in EC50 causes less than a 1% error in efficiency because you're taking the ratio of logs, and it turns out to be very robust. You can have significant errors in EC50 and it will give you the right efficiency. And if we go to these wholesale currents, where you get wholesale dose response curves, which are really different than the single channel dose response curves, you get pretty much the same efficiency. They're off by a little bit, but they're very accurate. So I think you can do a wholesale dose response curve. These have a 200 millisecond exchange time on that ion flux machine, and they gave us the right efficiencies, or approximately the right. So I think the answer is it's pretty insensitive.
Hey, can you, you're saying you have this catch state, and can you see any similarity between agonists that have similar catch states and or different catch? And can you rationally design or predict a certain compound that will have a certain catch
No,
from your data?
No, I think
Especially if you know the structures that are doing that.
No, we don't know the structural basis of catch. We don't know what that is. Number one. And number two, within each efficiency family, you have a wide range of catch. This is catch. If I go back to this slide, this is catch here. This is the catch energy right here. And within each family, you have a wide range of catch energies. Let's say between the red and the black, where we have most data. And so you can't really tell from efficiency or from agonist structure or anything about KD I can't predict KD from structure. It's in the on rate. All I know is it's probably going to be in the on rate of catch is what's the difference in the affinity, not in the off rate. So if you can, but I don't know how to measure on rate from structure. So I can't tell you anything about the structural basis of catch. And I think if I was a computational person, I would want to know what catch was and what the structural basis of catch was, because that's what you want to do when you want to scan things in silico. You want to scan the on rate, not the off rate. And right now people are scanning the off rate because they know how to do docking. Doing entry into the binding site is much more difficult. You have to calculate a potential mean force of the ligand moving down. You have to define a reaction coordinate. It's a very difficult problem to put a ligand into a binding site. It's an easier problem to measure the stability of a ligand once it's in that binding site, which is what people are doing. But I think that's a good question, Tom, that catches what you want to know. And in fact, I'll just say one thing. If you know the on rate, if you know K on, you know everything. If you know K on, I can tell you the entire dose response curve just from K on. This is everything right here. If you tell me this number here, I can tell you EC50, I can tell you everything, because everything is coupled by these linear for energy relationships. So K on is the beginning, and K on starts this whole chain moving. I'm talking too much here, but this thing, when the agonist shows up, it pulls down catch. And then everything follows. Everything just falls down. It's like dominoes or a zipper. I don't know what the word is. That things just fall down in these linear free energy relationships. That all you got to know is how much the agonist pulls down. You don't even have to know catch. All you have to know is the transition state to catch. If you can measure what agonists are doing to the transition state to catch, you know this entire process. So I think you've actually put your finger on the key point, on a key point. But I don't know what it is.
Okay,
Is
are there
that
any
it?
questions?
Mark has a question.
Oh,
Hi,
Mark.
Tony. I've got a really simple question. So you mentioned earlier that the concept of efficiency was developed with regard to steam engines. How impressive is 50% compared to the world of engines that we know of today?
Yeah, it's for chemical mechanical conversion, it's a little bit higher. I think if you go to Wikipedia, there's a whole table of conversion, energy conversion efficiencies. And electrical stuff is more like 70 or even 90%, but chemical to mechanical, like an automobile, is 35% to 50%. That's a chemical mechanical conversion efficiency. So it's a little bit higher than a car, but it's in the range. If you look at the range of conversion efficiencies, 50% is okay. It's not unusual. I will say also that there's a limit to what you can measure in conversion efficiencies. If you have a very, very low efficiency or very, very high efficiency, you're going to have to get picomolar sensitivity, picomolar or femtomolar binding affinities, which is not physically feasible with a small molecule binding to a protein. I don't think you're going to get tetramethyl ammonium to bind to a binding site, anything with femtomolar affinity, any protein. So there is sort of a range of efficiencies that's possible just based on physical chemical properties of ligands. But 50% seems to be a reasonable value for chemical mechanical, or from chemical to kinetic is what they call it in Wikipedia. That's my only source. I think Ken Dill did a compilation of energy efficiency, conversion efficiencies in enzymes, and I think they're in myosin, things like that. I think they're also in the range of 40–50%. Does that answer your question, Mark?
It does. Thank you very much.
Is that it?
Tony,
Yeah.
Randy.
it's a really nice study. I like it a lot. You got 4 different quotes unquote families of efficiencies though.
Yeah.
And so is the hypothesis for that there are perhaps 4 different open channel conformations? They may not be electrically visible as conductance changes, but perhaps torsional changes in some of the alpha subunits?
No, I don't think there's 4 different global conformational changes. I think within the gating conformational change, there are substructures. That goes back to that 5-value slide. So I think if you look, let me go back down to this slide. So within gating, going from C to O, you have these blocks of domains that keel over in sequence. So hold goes to twist, goes to tilt, rip, pop. That's that linear free energy linkage at the end. And I think that what different efficiencies reflect is different conformations of this substructure here, not the entire protein. That the binding site can go to different target sites inside that conformational change. Once that thing happens, I don't know, it's possible that this thing goes to a different structure and this goes to a different structure and that, they all go to a different structure. But my suspicion is that this thing, the rest of the conformational way stays the same, since it doesn't depend on the agonist. The only thing that depends on the agonist is the stuff near the binding site. So yes, as the way you put it, there are different structures, but I think these structures are local parts of the binding there are domains inside the protein that can take on different structures that give you different efficiencies. But in terms of the global structure, I would say that's probably the same. So we don't see we see a few, but we don't see very many subconductant states in this protein.
I wasn't talking about subconductant states. I mean, an open hole can be, an open hole. I'm just talking about perhaps subtle twists.
Yes.
In the rigid structures much further down, because you've discretized the whole efficiency thing across a wide variety of molecules that in that pocket are going to have very coarse changes in how they interact with it. You got a rather precise set of efficiencies, and that implies a very precise process that's maybe not as variable as the chemicals that you're putting in it to it.
Yeah,
that's why I'm saying remote might be better.
Yeah, so I think that if I were to imagine in the future when we have infinite number of structures that we're with different agonists, that we're going to see the structure of a open channel with epibadidine compared to the structure of an open channel with acetylcholine will be different, but the difference is going to be focused on the binding pocket. So I think the major structural difference between them will be localized to the binding pocket, and then as you get further away, it's going to be more and more the same. That would be my suspicion, although I have no data for that. And the answer to that is through structure and MD. And right now, neither of those are ready for prime time in terms of comparing with this energy map. As I say, it's going to take 40 years before this model is going to be. And if there's anybody out there who does ACH receptors, please do not ignore this data. Whatever model you come up with gating, when you publish a paper, you must be able to explain this data. This is a huge, solid data set that must be explained. And if you don't like our explanation, come up with your own, but don't ignore the data. If there's anybody out there working on ACH receptors.
So how would you determine the difference between whether it's a localized change up top versus so you say it's going to be a very specific change up top and very similar down below.
Yeah.
How would you distinguish between one that's a very coarse set of different changes up top that sort of get binned into 4 separate groups lower down? How would you do that?
You do it through X-ray crystallography and MD simulations is the only way I know. I don't think I could do that with the tools I have available to me, which are kinetics. I don't think I could tell where that is. I think it's remarkable that you can use kinetics to do anything to do with structure whatsoever. And this is sort of coarse. This map that we have is a very coarse map of the conformational changes. But I think the answer is going to come from structure and MD, and that'll take a long time.
Hey, Tony, as you remember, we looked to see if there were mechanical changes in the acetylcholine receptor kinetics, and there weren't. Which
there were or weren't?
Were not. There were none.
Right.
Which to me suggests that the conformational changes between open and closed, or any subset of those, are not particularly big in the membrane domain.
Absolutely. This is a hydrophobic switch down here that all it takes is we've been studying this region down here, and it just takes an angstrom movement of a side chain in order to open and close this water conduction pathway.
Yeah.
You do not need large scale changes in structure. Just a slight perturbation of the helices is enough to switch the thing on and off. This is a very delicate hair trigger switch, and it's based on hydrophobicity of a very narrow region inside the pore. So a very small region inside the pore, the hydrophobicity index of that is what determines whether you have water or nothing in there.
Yep.
I think more interesting, Fred, is your idea that when there's nothing in there, there's a Casimir effect, and that the vacuum energy is what's holding the channel closed.
Yeah.
That would be interesting.
A little quantum electrodynamics and
Yeah.
electrophysiology.
Yeah, that would be nice. But I agree. It's a tiny conformational change down here is enough to turn the thing on and off.
Yeah, right.
I have a question. So Tony, a very nice concept. So so if we think about the system, we have the binding energy differences in two states, and then part of the energy is used to switch the transmembrane domain. The other part, well, must be dissipated in a way. Is it possible to do some kind of heat-based measurement to actually test this dissipated part of the energy?
I don't know. I guess if you did isothermal calorimetry, you might be able to get entropy and enthalpy, break down these energies into enthalpy and entropy, but I can't answer that question. That's over my head right now.
Yeah, also related, you know, regarding the cavity contraction and opening,
Yeah.
the concept of induced fit in the binding site. One thing would be, you know, how about the freedom of water molecules, or the binding actually liberate a significant number of water molecules from there.
Yes.
And that makes your system an open system because of the exchange of water molecules with the environment.
Mm.
Would that be a significant contribution to your energy change in terms of the
yeah, it could be. I don't know the answer to that one either. That one, however, is experimentally testable by changing the osmolarity of the outside solution. So making it harder or easier to move water molecules in and out of the binding pocket using a large something to change the osmotic strength externally that can't get in the binding site. Something big, like dextran or something like that. So that's a testable hypothesis that the water motion is involved in this. And yes, I'm sure it's part of the system, and I'm sure it's part of the free energy exchange, and I'm sure it's part of the efficiency. It may not just be volume of the binding site. And in fact, the volume of the binding site is sort of like, I don't know what that is. I think ultimately it's going to boil down to conformational dynamics and understanding exactly what's happening to all the bonds and hydrogen bonds and everything else that's going on inside the binding pocket. The volume may be a first order approximation, and it may be some very specific changes in specific residues and bonds inside that binding pocket that's responsible for efficiency. But I think the van der Waals hypothesis is the one we want to test first, that steric bumping is what's limiting the contraction of the pocket.
Right. The ordering of the water and the freedom or the entropy related to that is going to be bigger in any energetic term probably.
Yeah, I think that's a good experiment, is to work on the water.
Okay, thank you. Very nice.
Is that it?
All right, thanks, Tony. Yeah, could be. Anyone else want to raise their hand?
Tony, This is Sasha Sobolevsky.
Sasha, how you doing?
Have you start thinking about mechanosensitive and temperature sensitive channels? What's gonna happen there? What's gonna be different?
Well, I will say that efficiency equation, let me just say that equation for efficiency, that simple equation, 1 minus the energy ratio, is going to pertain to voltage gated channels. It's going to be 1 minus the charge, the exposed charge in open versus close is going to be the efficiency of a voltage sensor. And even though you don't have different agonists, the stimulus is not so flexible. You got voltage is all you got to go by. But if efficiency is used to mark conformational change pathways, then maybe you would want to measure the efficiency of a voltage sensor. Same thing with mechanical. I mean, you have I don't understand mechanical channels, or temperature channels. So you're going to have to ask Fung about that. I think there's going to be an efficiency for any channel, and how you get that out of your channel. If it's area exposure, 1 minus the exposed area ratio, what the energy is coming into the open versus the close. But I think you're going to have the same equation. I think that equation is basically a general equation of efficiency of anything. And if you can figure out what the correlate of binding energy is, and I think it's QV for voltage, and I don't know, it's area, Fred, I don't know what it is for mechanosensitive, and for temperature dependent, maybe something completely different. But I think the capsaicin site on those temperature sensors is a good site to be probed if you have different agonists. But is that what you're asking, Sasha? That how do you translate this to?
Yeah, and in particular the discreteness, right, which you have on the both sides, right?
Yeah.
Do you expect some sort of discrete kind of initiation of gating with different stimuli?
Yes. The answer is I expect it because the ACH receptor is a model receptor. It is a model ion channel. And it's the first one for this has been found. So again, I would expect it to happen in other ones. The S4 section is going to have discrete target open channel conformations. It's going to start in a closed channel conformation, and it's going to go to different discrete open channel conformations, which change with I don't know what. So I would expect that in mechanical channels. I expect that in any kind of sensor, that the sensor can adopt discrete states, and those discrete states are going to be like a spectrum for the sensor. And different binding sites and different sensors are going to have different efficiencies, and efficiency is the thing you want to measure. So yes, I would think that it's typical, although I have no data. I can't predict. I wouldn't bet a lot of money, but I think that's what's going to happen.
Thank you, Tony. Very nice.
Yeah, thanks, Sasha. Nobody else?
Well, if I may, just one comment regarding voltage gating channels. I don't know how that's going to work out because, as far as we know, voltage gated channels are not allosteric, right?
No, they are, Leon. I think that the mistake made by the voltage gated people in general, which I don't want to get into an argument with because I will lose, is that the gating currents are not the sensor. That the gating currents are part, just like the binding site of hold. Gating currents are like hold. They are the hold event inside of gating, where things move. But anything in an allosteric cycle, the horizontal, the equivalent to binding is the deposition of energy from the external environment, and the vertical lines are the motion of the protein. And gating currents involve the motion of the protein. So it's like hold giving you a signal, but the energy that's coming into the channel is not the same as the gating currents. The energy coming into the channel is maybe it's the Paquito or something like that, something hard to measure. It's VQ, and Q is the charge that's exposed on S4. So I think you may not be able to get it at electrophysiologically, but you may be able to get it through structure or MD, that the exposed charge is going to be different in the open versus the closed. So I think they are allosteric, and if you go to zero voltage, you have an L0. I mean, BK channels are allosteric. That works fine. They're a potassium voltage gated potassium channel. So I don't quite understand the problem, why they're not, why MWC doesn't work.
Right. Well, I mean, when you measure if you try to measure the L0, right, you
Yeah.
go to really negative voltages.
No,
and,
no.
and-
L0 is zero environmental energy. L0 is what you get when there is no environmental energy, which is 0 millivolts. Go to millivolts, 0 millivolts, and measure the equilibrium constant. That's L0. You can change it with going plus and minus in voltage, whereas with ligands, you can only go plus by adding a ligand. You can go plus and minus, but the L0 is 0 environmental energy, which is a number, which is a big number, actually. You know, it's easy to measure at 0 millivolts, right? What's the equilibrium constant at 0 millivolts? Some big number. What's the probability of being open at 0 millivolts for one of these channels? Like 0.2 or 0.3? It's
yeah,
quite
right. Yeah, sure, but at 0 millivolts, you already moved a bunch of the charge, right? Almost all of the charge.
You've what?
At 0 millivolts, you already moved most of the charge, right?
Doesn't matter. 0 millivolts, whatever charge moves. That's 0 millivolts. That's part of L0. L0 means 0 environmental energy. That means you go into like no agonist, no voltage, no mechanical deformation. You know, this
So what you mean is that you need to go to really negative potential, not zero. Need to go to very high polarized potential to immobilize the sensor.
no,
Not a 0 millivolts.
I
Yeah,
don't
exactly.
see it that way. I think 0 millivolts determines L0. The
No,
definition of
no,
L0.
No,
no. You need to go to yeah,
right.
very negative potentials.
I don't think so.
that's right.
I disagree with that. We can talk about that, Fung. I could be wrong, but to me, L0 means no environmental energy. Nothing coming into the system. Let the system run. That's 0 millivolts. And
Well, in negative, in your case, L0 is in the absence of agonist binding. So in the voltage gated channels, L0 means in the voltage sensor has not been moved.
no, no. L0 means you haven't added any energy to the system. You can do negative and positive with voltage, and you can't do that with ligands. You can't go to less than zero with ligands. So I only have the option of adding energy. You guys have the option of taking it away or adding it, but you're starting at 0. That's the 0. L0 is 0 environmental energy. That's the way I think of it. So, and then, yeah.
Or it's probably equivalent to inverse agonist.
Well, an inverse agonist is doesn't take away later. It's one that stabilizes C more than O. So that's maybe an inverse agonist. I'm not sure. I don't know. Let's end this. I'm getting tired. I want to have a glass of wine. Any other questions out there? How many people are still hanging in there? There's still 26 people here. Anybody else have anything to say? No? Tom?
Just good to see everybody. That's all.
Good to see everybody.
It is good.
I think I'm going to go to the biophysics meeting because I miss seeing everybody. That's the reason to go to these meetings. I haven't been in years, and I feel like I need to go to the biophysics meeting. So, okay.
I want to say hello to Carl. I saw him around. Haven't seen him for a long time.
Carl?
Eggleby.
Carl, you hear me? Phone here.
Okay, do that on your own time, Fung. This is being recorded.
Yeah, Tony, thanks for inviting everybody. That was great.
Okay, good. Thanks, Tom, for doing a great job organizing it.
Oh,
So we say
okay.
goodbye.
Thanks, everyone. I'll record. End the recording now, and I'll send it to anyone who wants it. Thanks.
All right. Thanks, Tom. Bye, everybody.
Bye.